My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 617. In this lecture, I will continue my discussion on AlexNet. Let's go back to the research paper. What is this research paper? ImageNet classification with deep convolutional neural networks. Since we understood the architecture, the activations that we just try to already we discussed architecture of AlexNet in our previous lecture, isn't it? The activations that were used in this research paper were ReLU. Remember, in 2012, ReLU was new concept, very new concept. The second very interesting concept is, what is the second one? Dropout. They used dropouts, which is also very new concept as of 2012. Very new concept. ReLU was a very successful concept. It's still used extensively till today. Dropout was also a very successful concept. We were still using ReLU and dropouts. This paper also used multiple GPUs to train, which is what we are doing today. You can see that this paper used multiple GPUs to train the model, isn't it? Actually, if you see this one, these three, ReLU, dropout, and GPUs, are very interesting stuff that AlexNet paper used, isn't it? AlexNet was one of the first big success story that used all these three concepts. What are those three concepts? ReLU, dropout, and GPUs. But this is important. There is also one concept which is there is called local response normalization. This is also called as LRN. It's a concept that is introduced as a part of this research paper, but it did not stand the test of time. People eventually said LRN really doesn't matter. It's not that important. LRN is really doesn't matter, and people started using stuff like batch normalization, isn't it? Let's understand what LRN does. So imagine if you have a 3D tensor. We'll try to understand what LRN does. Imagine if you have a 3D tensor. For every pixel here, just let me assume I have a pixel here. For every pixel here, you have bunch of pixels behind it, isn't it? One on the behind it in the sense on the depth angle. Imagine this is 26 by 26 by 128 3D tensor. This is one pixel. This one pixel has 128 pixels behind it. Means including that pixel, you have 128 pixels. If you take this and write it down as a vector, you will get a vector of size 128. This is a pixel and all the pixels which is behind it, that is in depth angle. You normalize this vector. If you normalize all the depth vectors, you can think this vector as a channel. If you normalize each of the channel, this is simple normalization, like normalizing a vector. So you perform simple normalization of a vector, but instead of normalizing the whole tensor, this is important. Instead of normalizing whole tensor, we are only normalizing each of these vectors. This is called local response normalization. Today we don't use that anymore. Actually, even if you don't have local response normalization, things work fairly well. Today we have better normalization techniques like batch normalization. This is local response, I can say just see, today we have better normalization techniques like batch normalization, isn't it? I can say this is local response normalization part of this research paper. Don't worry too much about mathematics. Just you may here you have an equation. Don't worry about this particular equation. It is simple normalization on channels. So training on multiple GPUs, there is also ReLU nonlinearity. Just see, it is simple normalization on channels. Training on, you can see these concepts in this particular paper, training on multiple GPUs. There is also ReLU nonlinearity, isn't it? They also used pooling, isn't it? Just overlap pooling. There is a even you can see there is a data augmentation. Remember, we talked about data augmentation. They also used dropouts. Still we are using ReLU dropout. I can say we are using ReLU's dropout GPUs and the data augmentation. It will also point you to some point you to some code written by students. I think it is lecture notes, maybe it is a lecture notes in Yale University by statistics department where they taught this. Please note that this is not exact implementation of AlexNet. This is slightly modified implementation of AlexNet. Instead of doing this for 1000 class classification, this is simple code. Instead of 1000 class ImageNet problem, this sample code is on MNIST. This particular sample code is an MNIST dataset. Just see how simple it is. This is your, I can say this is your layer 1. You have convolution followed by activation followed by max pooling, convolution, activation, max pooling, isn't it? Yes, you can see in layer 3 also convolution, max actually in this case what you are using, something like you are doing model.add zero padding, isn't it? Convolution, model.add convolution, model.add activation, isn't it? Model.add activation ReLU. Then you are doing something like flatten, dense. Just you can see model.add flatten, model.add dense, model.add activation, model.add dropouts, isn't it? If you have this diagram, you can convert into code. This is code form of, if you have this particular diagram, you can write the code. This is code form of this diagram, isn't it? You can convert. If you have this diagram, you can convert into code. That's the important. Yes, I will repeat. If you have this diagram, you can convert it into code and run the code. You can easily convert into the code. At the end of it, you will compile. At the end of it, what you will do? Model dot compile, isn't it? At the end of it, you will compile with whatever optimizer you want. Yes, RMS prop is an optimizer, isn't it? You will compile with whatever optimizer you want and then fit, model.fit. And it's that simple, very simplified version of MNIST. Very simple. This paper has been, I can say this paper has been seminal except for LRN. Every other concept that is used in this paper to solve the ImageNet problem. Just go through this. If you have any difficulty, please keep a comment. Thank you very much.